Good morning to everyone. I am Lam Chi Hui from UTHM JTK EBNF. I've done the development of facial emotions and drowsiness detection system via Generative Adversarial Network as my final year project. Before my presentation, please allow me to ask you two questions. First, do you ever fall asleep when you're doing something? Second, do you ever affected by your emotion when you're doing something? I believe that most of you will answer yes for both questions. So, do these behaviors affect us while we are driving? The answer is definitely yes. Emotion aggression and sleep deprivation are highly correlated with road accidents. Hence, facial emotions and drowsiness detection system has great potential as a new form of assistant in monitoring driving. In this work, Generative Adversarial Network, in short, GAN, is used to generate photorealistic happy and neutral human faces. 200 GAN-generated happy and neutral human faces, 200 angry and sad human faces filtered from FER 2013 dataset, and 200 closed and open eyes images selected from MRL Eyes 2018 dataset are employed to train the model. Subsequently, a convolutional neural network model, in short, CNN, is used to conduct the facial emotions and drowsiness detection system for image and real-time webcam input. For the detection, image acquisition, region of interest, in short, ROI, detection with Haar Cascade algorithms, face and eyes abstraction, and prediction of emotion and eye states are done in turn. An average of 55% accuracy is achieved for the facial emotions detection system for image input, while 65% for video input. Also, 100% accuracy is achieved for the entire drowsiness detection system. For the background of study, emotion recognition and drowsiness detection are extensively implemented in the field of computer science. Network development and system training with dataset are common. Algorithms are employed to boost the system. The main concern of this work is the sentiment and tiredness of the driver to ease the development of Advanced Driver Assistance System, ADAS. The model should accept input capriciousness, complex calculation while performing accurate and fast prediction, and empower easier integration to the current existing system. For the literature review, facial emotion is discussed as the cheapest but fastest way for communication and interaction between humans. Meanwhile, drowsy happens when the driver drove with an exhaust state and concomitant wall behaviors such as dropping eyelids. Experiment with electroencephalography, electrooculogram, and electrocardiogram are not suitable anymore since they are disturbing. Hence, visual analysis with transfer learning, image processing, and computer vision technologies are emerged. These technologies can perform faster and higher precision computation with lesser training data and lower system complexity. For the methodology, the framework starts with transfer learning of style GAN to generate synthetic happy and neutral human faces with the generator model and further saved in Google Drive under Google Colab environment. Then, the model training and detection system are conducted under Jupyter Notebook environment. The model training starts with training data, which included the 400 images for each facial emotion and 200 images for closed and open eyes are imported from local files into the notebook. Image resized to 224 x 224 to fit the pre-trained models, and image to array conversion to represent the shape of the image with an HWC format. Next, the training data are created by append to concatenate the axis arrays. These training data are then shuffled, itemized, reshaped to 224 x 224 x 3 to again fit the pre-trained model, normalize to standardize the parameters, and maximize the speed and precision, and pickle to convert and access the object with the binary format in reading and writing. Next, the layers for the pre-trained model are adjusted to perform the appropriate classifications. Then, the model is further trained with different algorithms to perform the appropriate probability distribution, such as rectified linear unit value and softmax activation function to eliminate negative output while performing multinomial probability distribution, or sigma activation function to perform binary classification. Besides, sparse categorical cross-entropy is applied to enable mutually exclusive output, whereas ADAM optimizer is used to compatible with the sparse. Epochs are used to train the model repeatedly. After saving the model is loaded. Images are acquired from the input image, while frame and color space conversion are done to convert the input to grayscale as the training data. Next, ROI detections start with rectangular Haar Cascade classifier. Finally, the predictions start. Now, the presentation continues with the demonstration of the facial emotions and classification system. For image input, when the facial emotion detection model and image are loaded, Haar Cascade frontal face is used to detect the face. Prediction is done with arguments of the maxima, which take the maximum function value of the calculation as the output. The classes are differentiated from angry, happy, neutral, and sad emotion from 0 to 3. Hence, 0 is correspond to angry, 1 is correspond to happy, 2 is correspond to neutral, and 3 is correspond to sad. Then, the drowsiness detection model is loaded, and Haar Cascade eye is used to detect the eye. Prediction is done with binary distribution, which have only values between 0 and 1. The classes are differentiated from closed eye to open eye from 0 to 1. When the value is closer to 0, it is correspond to closed eyes. While the value is close to 1, it is correspond to open eye. Next, this is the output achieved for real-time webcam input. When angry or sad face detected, the alarm will turn on directly while skipping the eye detection. This is because negative emotions are already not suitable for driving. On the other hand, when neutral and happy faces are detected, it will be continued with drowsiness detection. When the eyes are open, the alarm would not turn on and the detection continue. But when the eyes are closed, the alarm would turn on and warn the driver. For the accuracy of the system with image, the face ROI and eye ROI detections are performed well. On the other hand, the facial emotions detection system is moderate while the drowsiness detection system is excellent. The accuracy for closed eye and open eye states are 100%. Meanwhile, the accuracy for angry and sad emotions are 40%, neutral is 60%, and happy is 80%. The average accuracy of the entire system is 55%. The lower precision on angry and sad facial emotion detection may be due to the minor difference between the expressions. When the face emotion shows obvious peculiarities, such as a bright smile for a happy face, the model can perform better. Besides, the lower precision may be due to inadequate model training. It should be related to the epoch and data diversity. The model should train with a higher epoch to increase the number of repetitions of the training to allow better learning. Meanwhile, The comprehensiveness of the training data of each emotion should be improved since each emotion can be expressed in myriad ways. But this action will fuse the difference between each emotion. Hence, the filter of the training data is crucial. For the accuracy of the system and alarm with webcam, predictions of the facial emotions are performed better. The testing set is reused to ease the comparison of the performance of the model. The accuracy for drowsiness detection and alarm are 100%. Meanwhile, for the accuracy for angry, sad, and neutral emotions are 60%, while happy is 80%. The average accuracy of the entire system is 65%. The difference for the image and webcam input may be caused by the looping of the detection system. Real human expressions may not be static as the images. The fine changes of the current input are updated and calculated constantly by the model to perform a better prediction. Hence, better performance is achieved. The two main limitations for this work during the image acquisition are it required a clear input without obstacle around the feature, and it required a complete feature input. Hence, inputs with makeup and spectacles would affect the detection process, as well as the inputs with a covered face and mask. Additional algorithms are necessary to overcome these drawbacks. When the current work is compared with previous work, the performance of the development of the facial emotion and drowsiness detection system currently are satisfying. The disability of the drowsiness to detect eyes over glasses is explained and discussed previously. The outstanding performance from Jaiswal, Raju, and Deb is due to the qualitative and quantitative dataset from JAFFE and FERC 2013 dataset, along with the implementation of GPU 400 of epoch in model training, as well as the design of layers, learning rate, and momentum that are compatible with each other to achieve ideal recognition rate. In conclusion, ADAS was developed with rapid progress along with the growth of autonomous cars over time. Hence, facial emotions and drowsiness detection system has high demand in monitoring driving to reduce the number of road accidents caused by emotional aggression and sleep deprivation. This work developed facial emotions and drowsiness detection system that utilize GAN and CNN with image processing and computer vision technologies to collaborate with pre-trained models and algorithms to detect the random image and real-time webcam input. The model detection system empowered satisfying ROI detections and reliable predictions with high accuracy. These are the references involved in this presentation. Thank you.